The solid tool post mount holds the quick change rigidly in position and replaces the compound. The compound has multiple degrees of freedom. It can rotate here, move along this axis. The quick change can rotate around the tool post stud, and the entire compound can move along the cross slide if the compound studs are not tight. This makes the compound one of the weaker spots of the lathe. And the SouthBend design is especially weak because of the small diameter post that the compound rests on. During a heavy cut, you can actually see the compound flexing. And that flexing with a tool like this cutoff tool causes it to gouge the material and the spindle to stall and the machine to crash. The solid tool post solves that by being a single piece of cast iron, and it presses into the side of the quick change, preventing it from rotating. The second reason to replace the compound is to accommodate larger tools. When I installed the Aloris AXA onto this compound, I milled out this area to lower 3/8 inch tools down to the center line of the spindle. Now I want to use 1/2 inch tools, and to do that I'd have to cut this out even more. This design is inspired by Robin Rossetti's original video on the solid tool post mount. He has a couple additional features. He adds a pin here for positive registration of the quick change, and a slope on this side for chips to fall off. The second video that I got inspiration from is Stefan Gotz's Venters, and he didn't include this boss. Instead, he uses a small piece of steel to press and hold the quick change in position, and then he pins that piece of steel. The third video is probably the most ambitious and certainly the coolest, and that's Vic Rivers of Rivers Company. And he replaced not only the compound but the cross slide as well, making them one integrated piece. 3D printed that design with the intention of later casting it. The solid tool post mount is made from a single piece of gray iron, and it's a type of cast iron that absorbs vibration well. The first thing I do is to square up the stock and then take it to size. To fill any gaps between the vise and the stock, I'm using a piece of aluminum rod that gets compressed. And as a surface is faced, then it'll be rotated toward one of the sides of the vise. Now two sides are faced, and those go against the fixed and movable jaws, and the irregular side is facing down. Square it up best we can on this side, squeeze it in the vise, and continue. When I first started this, I used the fly cutter at its maximum swing, and there was a lot of vibration just because of the lack of rigidity in the fly cutter. I made this small program to make 3 passes, that is half of the fly cutter on the front, half on the back, and then the middle, all coming from the same direction. And this will leave 3 high places if the mill is out of tram that can easily be knocked down on the surface plate. With a small program to chamfer 2 edges, rotating the block, and resetting the origin, that's all that's really necessary in order to chamfer all the edges of the block. This is a 9mm drill. A lot of people say to mill cast iron without any sort of lubricant or coolant, but you can see that these chips are pretty hot. Maybe it's the graphite content that's assumed to provide lubrication, but the tool and workpiece still get hot, so seems reasonable to use coolant on cast iron. And it also seems to control the dust a little. This is a 1/2 inch end mill running at 1500 RPM, 17mm depth of cut, and 10,000ths of an inch step over. The G-code was generated in Fusion 360, and this is a 2D adaptive clearing operation with both ways enabled. And for the most part, milling the cast iron was pretty easy. You can see a lot of flakes being kicked out from the mill, and there's small iron particles that are floating in the air. You can see how they attach to this magnet on the side of the mill. That circle you saw on the magnet is actually where the quill used to be attached, and I removed that, filled it with body putty. And this is a corner clearance for the Aloris quick change. And this is the thread mill making the 9/16 inch, 18 threads per inch thread for the tool post stud. It's a single profile thread mill, and the nice thing about the single profile thread mills is that you can do a variety of sizes and thread pitches. All the edges are getting chamfered, and this gets chamfered to the major diameter of the thread. And this helps a screw to start easily. Another nice thing about the thread mill is I'm practically able to bring that thread mill to the bottom of the hole. I don't need to have a lot of clearance at the bottom for a tap. With the quick change mounted, I want to be able to slide the tool holders past the bottom just slightly in case I need that extra range. I'm just verifying that I got the measurements right. These holes will be tapped to receive set screws that push against the quick change to prevent it from rotating. I chamfer the bottom of these counterbore holes so that the socket head cap screw doesn't interfere with the hole. Now I'm starting to work on the T-nuts and have sized the 4 larger sides and am making the grooves to turn this into the T-shape. This was made from cold rolled steel stock, and unfortunately when I took it out of the vise it turned into this smile shape. I cut this up into 4 pieces and then just began to clean that up. This is a 6.7 millimeter drill for threading this hole to 8 millimeters. With single profile thread mills you have to run the thread mill the entire length of the thread, but with multi-profile thread mills you only need to make 1 rotation to cut all of the threads. To use these you have to run the program slower to give the tool plenty of time to cut, because it is cutting more than with a single profile thread mill. I want the T-nuts to fit snug in the slot, and the 20 thousandths of an inch radius of the 1/2 inch end mill is just enough that creates interference. And so this is a square end mill that's being used to clean up that radius. In this picture, the part with the radius corners is on the right and the part with the square corners is on the left. And you can see how with the square corners they really made up well. This is a neat comparison between 3 different threads. The top center is thread milled, bottom left is tapped, and then bottom right is a hex nut. And just compare the amount of wiggle after the screw is inserted the same distance. First loosen the nut on top of the tool post stud. Remove the quick change, set aside, loosen the nuts on either side of the compound, slide the compound off. Next you install the T-nuts into the T-slots, and these new T-nuts are threaded down to 20 thousandths of an inch above the bottom of the T-nut, and that's to keep longer screws from ever being used and jacking the T-nut up against the bottom of the T-slot and breaking it out. 8 millimeter screws secure the solid tool post mount into place. And the mill did a fine job on the surface finish, but of course the shininess comes from work with sandpaper, the surface plate, and then a little bit of polish. Make sure the bottom of the quick change is clean. And then tighten the set screws. The set screws are flat faced so they don't mar the quick change. And I think I'll add a second set screw behind each of these to lock the set screws pressing against the quick change into position. Alright, thank you for watching. Let me know what you think of this project, and I'll see you again on the next video.